Here is a question that sounds like it belongs in a Marvel movie, but turns out to be taken completely seriously by some of the most decorated physicists alive. How many multiverses are there? Not how many universes, multiverses. And that distinction is doing a lot of work. A multiverse is already supposed to contain everything. It's supposed to be the full set, the grand total, the complete collection of all that exists. So asking how many of them there are feels a bit like asking how many totalities there are. It sounds like a paradox. It sounds like the kind of thing that gets you thrown out of a philosophy seminar. And yet here we are, in the early 21st century, with serious papers in serious journals exploring precisely this question, not because physicists have lost their minds, but because several of the most successful and carefully tested theories in science, when you follow their logic all the way to its conclusion, point insistently in this direction. The other universes weren't what anyone was looking for. They showed up anyway as a mathematical consequence of equations that physicists developed to explain something else entirely. The word multiverse gets thrown around constantly now. It's in blockbuster films, television series, comic books, and video games. Most people's mental image of it involves alternate versions of themselves making different choices. A version that took the other job, stayed in the other city, or said something different at the moment that mattered most. That picture is not entirely wrong, and there is a respectable scientific framework that edges towards something like it. But the real science of the multiverse is stranger, more varied, and in many ways more unsettling than anything Hollywood has managed to put on screen. It also turns out that there isn't one version of the multiverse. There are at least 4 scientifically distinct frameworks, each arising from a different area of physics, each with its own implications about how many other realities exist, what they're made of, and whether we could ever detect them. In some versions, the other universes are identical to ours. In others, they have completely different laws of physics. In others still, they operate according to mathematical rules that have nothing in common with anything we've ever observed. The answers to how many multiverses are there range from 0 to 1 to infinite, depending entirely on which version of the physics turns out to be right. What we're going to do is start where we actually are, the bubble of space we can see, and work outward through each layer of the idea, exploring the physics that drives it, the scientists who developed it, and what it would mean for the nature of reality if any of it is true. But first, it helps to know that this isn't actually a new idea. The intuition that our universe might not be the only one is ancient, and the people who argued for it paid serious prices for doing so. In 1584, an Italian friar named Giordano Bruno published a philosophical dialogue called De l'Infinito, Universo e Mondi, on the infinite universe and worlds. In it, he argued that the universe was infinite in extent, that the stars were distant suns like our own, and that those suns were orbited by worlds, many of which might be inhabited. He went further than most were willing to follow. He proposed that the universe had no center, no preferred location, no hierarchy. Everything was equivalent. The Earth was not special. The Sun was not special. Our particular arrangement of stars and planets was one instance among infinitely many. Bruno was not working from the mathematics of inflation or quantum mechanics. He was working from philosophical reasoning and a kind of fearless cosmological intuition. He was also, by the standards of his time, committing something very close to heresy. The Church was deeply invested in a cosmos that had a center and a purpose, a cosmos in which the Earth occupied a unique and privileged position, with humanity at the apex of creation. Bruno's infinite universe with its infinite worlds left no room for that picture. In 1600, after 8 years of imprisonment and trial by the Inquisition, Giordano Bruno was burned at the stake in the Campo dei Fiori in Rome. His books were placed on the Index of Forbidden Books. Exactly what charges contributed most to his execution remains a matter of historical debate. The trial records were largely destroyed, but his cosmological views were certainly among them. Bruno was not the first person to suggest multiple worlds. The ancient Greek philosopher Anaximander may have gestured at the idea in the 6th century BCE. The atomists, Leucippus and Democritus, proposed that the universe was infinite and contained infinitely many worlds, some with their own suns and moons. But Bruno brought the idea into the modern period with unusual specificity and force, and the cost he paid reflects how radically destabilizing it was to the prevailing worldview of the time. The idea that our universe is special, unique, central, the whole of existence, has been challenged and eroded at every step since then. Copernicus displaced the Earth from the center of the solar system in the 1540s. Galileo confirmed and extended that displacement with his telescope. Newton showed that the same laws of physics operate throughout the observable universe, that the stars aren't embedded in a divine celestial sphere obeying different rules, but are objects subject to the same gravity that governs apples and cannonballs. Hubble showed in the 1920s that the Milky Way is one galaxy among billions, each containing hundreds of billions of stars, spread across an expanding universe far larger than anyone had imagined. And now, in the 21st century, physicists are seriously exploring whether our entire universe, all 93 billion light-years of it, with its 2 trillion galaxies and its hundreds of billions of years of history, is itself just one instance among a vast or infinite ensemble. Bruno would have recognized the pattern, if not the mathematics. The question he asked with his life is the same one physicists are asking with equations. Is this really all there is? Before any of this can make sense, it helps to be clear about what the word universe actually means in physics, because it gets used in 2 different ways that matter enormously here, and confusing them leads directly to confusion about what the multiverse is and isn't. The first meaning is the observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels at a fixed speed. That means there is a distance beyond which, no matter how powerful a telescope we build, we simply cannot see. Not because something is blocking the view, not because the signal is too faint, but because the light from those regions hasn't had time to reach us yet. The universe hasn't been around long enough. That boundary sits at roughly 46 billion light-years in every direction from Earth, slightly more than you'd calculate from the age alone, because space itself has been expanding during the time that light was traveling, which carries distant galaxies further away as the light crosses toward us. The total diameter of the observable universe works out to about 93 billion light-years, containing roughly 2 trillion galaxies. Every star, every planet, every nebula, every supermassive black hole that astronomers have ever observed sits within that sphere. The cosmic horizon isn't a wall, and there's nothing special about it from the perspective of anyone who might be near it. If you could somehow teleport to the edge of our observable universe, you'd see exactly what you'd expect to see: space, galaxies, stars, extending in all directions. With another sphere of observable universe centered on your new position, you'd look back toward Earth and see it sitting at the edge of your new horizon. The horizon is relative to the observer, not a physical boundary in space. It's just the edge of what light has had time to reach. The second meaning of universe is the whole thing, everything that exists, whether we can see it or not. And this is where the conversation gets interesting, because the 2 meanings are often conflated in ways that muddy the debate about the multiverse enormously. The observable universe has a horizon not because space ends there, but because of the age and expansion history of the cosmos. Beyond that horizon, space almost certainly continues, and everything we've been able to observe on this side of the horizon strongly suggests that the space beyond it follows the same physical rules, contains the same kinds of matter, and is organized into the same kinds of structures. How do we know? The measurements of the cosmic microwave background radiation, the faint uniform glow that fills all of space, the afterglow of the Big Bang embedded in the fabric of the universe when it was about 380,000 years old, show no sign of curvature at the scale of the observable universe. If space were curved back on itself like the surface of a sphere, we'd see specific patterns in the CMB where some fluctuations would repeat around the back of the sphere. We don't see them. The maps of galaxy clustering show no sign of a boundary or edge. The spectrum of distant quasars shows the same physics operating in the very early universe as in ours today. Every observation is consistent with space simply extending beyond what we can see, following the same physical laws, filled with the same kinds of matter and structure. If that's true, if space is genuinely infinite or even just vastly larger than the observable region, then something mathematically inevitable follows. And it's the first version of the multiverse, the one that requires no exotic physics, no new theories, and no leaps of imagination beyond accepting that space might go on further than we can see. Max Tegmark is a Swedish-American cosmologist at MIT who has thought about these questions more systematically than almost anyone. He grew up in Stockholm, the son of a statistician and a teacher. As a physicist, he became known for not being afraid of ideas that made other scientists uncomfortable because he insisted on following mathematics wherever it led, and he was willing to write about the destinations openly. His framework for organizing the different types of multiverse into 4 levels of increasing strangeness has become the standard way physicists structure these discussions. The first level is also the simplest. Its logic says that our observable universe contains a finite amount of matter arranged in a finite number of configurations. The number of possible ways that matter can be arranged in a region of space the size of our observable universe is enormous. Tegmark estimates it at roughly 10 to the power of 10 to the power of 118 distinct quantum states. That's not a number you can write out in a reasonable amount of time or ever. The observable universe contains about 10 to the power of 80 atoms. Comparing 10 to the power of 80 to 10 to the power of 10 to the power of 118 is like comparing a single atom to the observable universe. The number of possible configurations is almost beyond imagination, but it is not infinite. And infinity is what matters here. If space is infinite, or even just very much larger than what we can see, then it is filled with an infinite number of regions the same size as our observable universe. These are sometimes called Hubble volumes, after Edwin Hubble, the American astronomer whose observations in the 1920s first showed that galaxies beyond the Milky Way exist, and that they're receding from us in a pattern consistent with an expanding universe. Hubble's observation is what first gave us the modern picture of the cosmos as having a beginning and an evolution. In an irony he never lived to appreciate, the implications of his work eventually led through inflation and eternal expansion to the idea that our observable region is one of infinitely many similar regions in a universe that dwarfs even what he could have imagined. With infinitely many Hubble volumes, each with a finite number of possible configurations, every possible configuration gets realized, not once, but infinitely many times. That's what infinity means. It doesn't leave gaps. With infinite rolls of the dice, not just every outcome occurs infinitely often. The universe doesn't run out of space to try every possibility and move on. It repeats every possibility endlessly in an infinite spatial tapestry. The implication is that somewhere out there, in ordinary space, simply very far away, there exists another region of the universe that contains a planet identical to Earth, with a civilization identical to ours, with a person identical to you, thinking thoughts identical to yours, at this exact moment, not similar, identical down to the arrangement of every atom, the firing of every neuron, the exact content of every memory. Tegmark estimates the nearest such copy is roughly 10 to the power of 10 to the power of 28 meters away, a distance so large it has no name, can't be meaningfully visualized, and will never be crossed by any signal or traveler. But it is a finite distance in a truly infinite universe. It's a mathematical consequence of basic combinatorics applied to an infinite spatial volume. There are also versions of you out there that are almost but not quite identical. A version whose history diverged from yours at some point in the past and has followed a different trajectory since. A version that made different choices, experienced different events, arrived at a different present moment. In an infinite universe, every version of you that's physically possible exists somewhere. Not all of them are alive. Not all of them are recognizably human. Some are versions where the history of the Earth diverged long before you were born, producing a world nothing like ours. The configurations span the full range of what's physically possible, from the almost identical to the completely alien. Of course, there is no way of ever reaching any of these distances, or receiving any signal from them, or confirming that these copies exist. They're beyond the cosmic horizon by a margin so vast that our best space probes, the fastest things humans have ever built, would need longer than the current age of the universe to cover even a tiny fraction of the distance. But the argument for their existence requires nothing beyond two premises: that space is infinite or very much larger than the observable region, and that physics works the same way out there as here. Both premises are consistent with everything we've observed. The Level 1 multiverse is the most conservative version of the idea, the multiverse you get for free without any new physics, simply by accepting that space goes on further than we can see. Most physicists don't lose much sleep over it, perhaps because its implications, though staggering, feel remote. The copies are too far away to matter in any practical sense. But as a conceptual foundation, as a demonstration that other universes doesn't have to mean exotic physics or impossible science fiction, it sets the stage for everything that follows. To understand where the second version of the multiverse comes from, we need to go back to a specific problem that was troubling physicists in the late 1970s, a problem with the Big Bang model that was elegant in its presentation but deeply stubborn in its resistance to easy solutions. And to understand the problem, we need to spend a moment with the man who solved it. Alan Guth is a soft-spoken physicist from New Brunswick, New Jersey. He studied at MIT as an undergraduate, got his PhD there, and then spent a decade moving through postdoctoral positions at Princeton, Columbia, Cornell, and Stanford. Academic physics is a competitive field where permanent positions are scarce and the pressure to produce original ideas is relentless. By 1979, Guth was 32 years old, older than many postdocs without a permanent position, working on problems in particle physics and cosmology that had not yet paid off in any attention-getting way. In December of 1979, working late at the Stanford Linear Accelerator Center on a problem related to magnetic monopoles, hypothetical particles predicted by grand unified theories that should have been produced in the early universe but have never been observed, Guth had a realization. He wrote 2 words in his notebook with a box around them. Spectacular realization. He underlined it twice. What he realized was that a period of extremely rapid early expansion would solve not just the magnetic monopole problem, but also 2 older and deeper puzzles that had been nagging at cosmologists for years. The first puzzle was called the horizon problem. When we map the temperature of the cosmic microwave background, which is the radiation left over from when the universe cooled enough for electrons and protons to combine into atoms, about 380,000 years after the Big Bang, we see that it has almost exactly the same temperature everywhere in the sky, 2.725 degrees Kelvin, with fluctuations of only about 1 part in 100,000. The sky looks the same whether you point your instruments north or south, east or west, toward any part of the sky in any direction. That uniformity is remarkable, and it presents a problem. 2 regions on opposite sides of the sky, let's say one region in the direction of Andromeda and another in the exact opposite direction, have never been in contact with each other. Given the speed of light and the age of the universe, they have always been too far apart for light or any other signal to have traveled between them. There was no way for them to exchange heat, to equilibrate, to agree on a temperature. Under the original Big Bang model, they had no mechanism for coordination, and yet they look identical. It's as if you found 2 sealed rooms on opposite sides of a continent, never connected to each other in any way since the beginning of time, and discovered that they contain air at precisely the same temperature. You'd want an explanation. The second puzzle was the flatness problem. Observations of the universe's large-scale structure show that space is geometrically flat, not curved back on itself like a sphere, not opening outward like a saddle, but flat in the way a plane is flat. Gravity, electromagnetic radiation, and light all travel through this space without bending due to spatial curvature. For the universe to be this flat today, calculations show that it would have needed to be extraordinarily precisely flat at the moment of the Big Bang, to about 1 part in 10 to the power of 60. Any tiny deviation from perfect flatness in those first moments would have been amplified by expansion into something enormous and catastrophic. A slightly positively curved early universe would have collapsed back on itself billions of years ago. A slightly negatively curved early universe would have expanded so fast that no structures would ever have formed. The fact that we find ourselves in a flat universe today means the initial conditions of the Big Bang would have had to be fine-tuned to a precision that seems almost impossible to accept as coincidence. Guth's solution was elegant. He proposed that in the first tiny fraction of a second after the Big Bang, in a time interval so small it defies any ordinary comparison, the universe underwent a period of exponential expansion driven by a field with very high energy density. Space stretched by an enormous factor in an extraordinarily brief moment. Conservative estimates put the minimum expansion factor at 10 to the power of 26. This resolved both problems simultaneously. The horizon problem disappears because all of the regions we can see today were once crammed into the same tiny, causally connected space before inflation tore them apart. They had time to reach the same temperature while they were still close enough for heat to flow freely between them. Then inflation stretched that uniform patch to cosmic scales, and the uniformity was preserved. The flatness problem disappears because any curvature that existed before inflation would have been stretched so completely smooth that it would be undetectable today, exactly the way the surface of a balloon becomes locally indistinguishable from a flat plane as you inflate it. An ant on the surface of an Earth-sized balloon would have no way of measuring the curvature of its world. Inflation does the same thing to the universe's geometry, just on a far more extreme scale. Inflation is not a speculative idea at the margins of cosmology. The specific statistical patterns of the fluctuations in the cosmic microwave background, the way the hot and cold spots are distributed across different angular scales, match the predictions of inflationary models with remarkable precision. The ESA's Planck satellite, which mapped the CMB in extraordinary detail and released its final results in 2018, found results entirely consistent with inflation's predictions. The BICEP and Keck collaborations at the South Pole have been searching for the specific type of polarization that some inflationary models predict, constraining the range of viable models significantly. Inflation, in its broad outlines, is treated by most cosmologists as essentially confirmed, even if the specific mechanism remains debated. The trouble is what happens when you push the theory's mathematics a little further than Guth originally needed to go. In 1983, Paul Steinhardt, one of the physicists who had contributed to developing inflation, worked out something unexpected in the theory's mathematics, and Alexander Vilenkin at Tufts University found the same thing independently, arriving from a different direction in the calculation. The mechanism driving inflation doesn't shut off all at once, everywhere simultaneously. It decays locally through a process driven by quantum fluctuations. Different regions of space stop inflating at different moments. While one region settles down into the hot, dense sea of particles we call the Big Bang, the surrounding space is still inflating, still stretching exponentially. And here's the key. In a region of space that's expanding exponentially, new inflating space is being created faster than existing space can decay into bubble universes. The inflation sustains itself. It creates more inflating space faster than bubbles form. The process doesn't stop. It keeps going indefinitely, generating new bubbles continuously, like foam that never settles. Vilenkin famously described it as a process of self-reproduction, the inflationary universe acting as a kind of cosmic engine that generates new universes faster than any of them can produce observers to count them. Alan Guth, who came back to MIT and has remained there ever since, has said that it's very hard to build models of inflation that don't lead to eternal inflation. Not impossible, but the simplest and most natural versions all point in the same direction. Once started, inflation tends to keep going. The models that avoid eternal inflation tend to be more complicated, more finely tuned, and less well motivated by the data than the ones that don't avoid it. This isn't a fringe view. Andre Linde at Stanford, who developed an influential variant of inflation called chaotic inflation in the 1980s, has been one of the most vocal proponents of eternal inflation for decades. Linde has described the universe as an eternally self-reproducing inflationary cosmos in which what we call the Big Bang was just one local event in a background of continuous creation. The picture this paints is one of the most unusual in all of science. The inflationary background isn't a place in any recognizable sense. Space inside it is expanding so rapidly that no particle, no signal, no structure could ever persist there. It's a domain of pure violent expansion filled with the energy of the inflaton field, with no stars, no galaxies, no atoms, and no physics as we understand it. Within this background, quantum fluctuations occasionally tip local regions into lower energy states, causing pockets of space to stop inflating and instead release their energy as radiation and particles. Each such pocket is a Big Bang. Each becomes a bubble universe. Our universe is one of those bubbles, expanding and cooling for 13.8 billion years inside a larger context that may have been inflating for incomparably longer, and that shows no sign of running down. The bubbles are separated from each other not by walls or barriers, but by inflating space that expands faster than any signal could ever cross it. This is a crucial point. It's not that the bubbles are simply very far apart, it's that the space between them is actively growing at a rate that outpaces light itself. No probe, no message, no gravitational wave could bridge the gap. From inside any given bubble, there is no way to look out and see the others. Each bubble is causally isolated, a completely self-contained island, surrounded by an inflationary ocean that is, as far as the physics indicates, infinite. What this means from the inside is worth sitting with. An intelligent being in any bubble universe, however different from ours, would look outward and see their own cosmic horizon. They would map their own CMB. They would derive their own laws of physics from the constants they observe. They would have no way of knowing that those laws are local features of their particular bubble rather than eternal truths about reality. In all relevant ways, their experience of the universe would feel as complete and coherent as ours feels to us. And if the physics in their bubble were significantly different, if the electron were heavier or the cosmological constant larger or nuclear fusion impossible, they simply wouldn't be there to observe it. This is the level 2 multiverse, and it comes with a consequence that makes it far more significant than the level 1 version. In the level 1 picture, every distant region of space follows the same physical laws as ours. Different histories, different arrangements of matter, but the same underlying physics. In the level 2 picture, the different bubbles can have different physics entirely. When the inflating field decays in a particular region and triggers that region's Big Bang, the exact state it settles into, its vacuum state, isn't necessarily the same from bubble to bubble. Think of it like water freezing. Given similar conditions, water can solidify into crystals of slightly different structures, depending on microscopic fluctuations at the moment of freezing. The same principle applies here, except what varies isn't crystal geometry, but the fundamental constants of nature. The strength of gravity, the mass of the electron, the cosmological constant, the ratio of the strong nuclear force to the electromagnetic force. These can all land on different values in different bubbles because they're determined by which energy minimum the field settles into, and quantum fluctuations make that landing point unpredictable. The differences can be enormous. Some bubbles collapse almost immediately after forming. Others expand so fast from the very start that matter never has the chance to clump under gravity, which means there would be no galaxies, no stars, and no chemistry. In still others, atoms might be unstable, or the nuclear reactions that build heavy elements inside stars might not work, leaving a universe composed almost entirely of hydrogen and helium with no carbon, no oxygen, and no foundation for biology. In most bubbles, by this picture, nothing interesting can happen. The vast majority of all bubble universes that have ever formed are empty, featureless, and entirely without event. Which leads directly to the question that has haunted physics for decades. If most possible universes are barren and lifeless, Why are we in one of the rare ones that work so extraordinarily well? There is a set of numbers written into the fabric of our universe, constants of nature that can't be derived from first principles but have to be measured experimentally: the strength of the electromagnetic force, the mass of the electron, the gravitational constant, the cosmological constant. These numbers sit at the foundation of every physical process, and they have specific values that, as far as current theory can tell, had no reason to be what they are. There's no equation that predicted them in advance. We measure them and accept what we find. What we find is unsettling. The cosmological constant, the energy density of empty space which drives the accelerating expansion of the universe, has a measured value of approximately 3 × 10 to the negative 122 in natural units. That's not quite zero, but it's extraordinarily close to it. The theoretical expectation, based on quantum field theory calculations, the same theoretical framework that has produced some of the most precisely verified predictions in all of science, is that it should be somewhere around 1. The discrepancy between the theoretical expectation and the observed value is 122 orders of magnitude. To put that in perspective, physicists have made predictions about the magnetic moment of the electron that match experiment to 11 decimal places. That kind of agreement is considered one of the greatest achievements of theoretical physics. The cosmological constant prediction is off by 122 powers of 10 in the opposite direction. It is the largest discrepancy between theory and observation in the history of physics, by an enormous margin. Physicists sometimes call it the worst prediction ever made by a physical theory, which is a remarkable thing to say about a theory that works so well in every other respect. Why does it matter? Because if the cosmological constant were even slightly larger than its actual value, the universe would have expanded so rapidly after the Big Bang that matter never had the chance to clump together under gravity into galaxies. Slightly more negative than it actually is, and the universe would have collapsed back on itself before any stars formed. The observed value sits in a narrow window, narrow by any measure, that allows the universe to evolve into the rich, complex, structured place we inhabit. And there is no known reason within existing physics for it to have landed there. In 1987, the Nobel laureate Steven Weinberg, who shared the 1979 prize for his work on unifying the electromagnetic and weak forces, published a paper arguing something that seemed almost philosophical at the time. He proposed that the cosmological constant is small because it has to be small for observers to exist. If it were much larger, there would be no galaxies, no stars, no planets, no observers. We find ourselves in a universe where the constant allows life, because in universes where it doesn't, there's nobody around to notice. This is the anthropic argument, and Weinberg noted explicitly that it's only meaningful if there are many universes with different values of the constant. He didn't invoke the multiverse because he wanted to. He invoked it because it was the only framework that gave the anthropic argument any explanatory force. 7 years before he wrote that paper, the idea of eternal inflation barely existed. The convergence of the cosmological constant problem and the multiverse solution, arriving from completely different directions, struck many physicists as significant. The story of fine-tuning begins even earlier, though, with one of the stranger episodes in 20th century physics. In 1953, Fred Hoyle, the British astrophysicist who coined the term Big Bang while dismissing the idea in a radio broadcast, not quite anticipating that the name would stick, was working on the problem of how carbon forms inside stars. Carbon is the basis of every biological molecule we know of. Life, as far as we can tell, requires it, and it's made in stars through a sequence of nuclear fusion reactions. Hoyle calculated that for the reaction that fuses 3 helium nuclei into a single carbon nucleus to happen at a rate fast enough to produce the carbon abundances we observe in the universe, the carbon-12 nucleus would need to have a specific excited energy level, what physicists call a resonance, at almost exactly the right value. Without it, the reaction would be too slow, and stars would produce almost no carbon at all. Hoyle predicted the value before it had been measured. When William Fowler's group at Caltech searched for it experimentally, they found it at essentially exactly the value Hoyle had calculated. Hoyle reportedly said afterwards that the universe looked like a put-up job. He never became religious in any conventional sense, but the precision of the carbon resonance and what it implied about how dependent life was on the fine details of nuclear physics never left him. Small changes to the strong nuclear force, or to the electromagnetic constant, or to the relative masses of protons and neutrons would shift that resonance enough to prevent carbon from forming efficiently in stars. And carbon isn't the only case. The stability of the hydrogen atom depends on the precise relationship between the masses of the proton and neutron. The fact that protons don't decay rapidly, at least not within the current age of the universe, depends on a specific set of relationships between the forces. The ability of stars to burn steadily over billions of years, long enough for planets to form and life to evolve, depends on the strength of gravity relative to the electromagnetic force being in a specific range. Each of these is a separate constant. Each of them sits at a value that allows complexity to exist. This is what physicists mean when they talk about a fine-tuned universe. Not that someone deliberately set the dials. That's a separate philosophical question that physics can't answer. But that the specific values of the constants look, by any statistical measure, as if they were drawn from a narrow acceptable range out of a much wider space of possible values. The probability of landing on life-permitting constants at random in a universe where constants are drawn from an arbitrary distribution seems by any straightforward reckoning to be very small. There are three responses available. The first, a deeper theory, will eventually show why the constants have to take these values, removing the appearance of fine-tuning the same way quantum mechanics removed the mystery of atomic energy levels that had seemed arbitrary to 19th century physicists. This is an optimistic and scientifically respectable position, but it requires finding that deeper theory, which hasn't happened in half a century of looking. The second, coincidence, which most physicists decline to accept as an explanation for something this precise across this many independent parameters. The third, the multiverse. The constants vary between universes, and we observe what we observe because we're in one of the rare instances where they work. The third response requires the multiverse. And the level 2 bubble picture, with its enormous variety of possible physics across an infinite ensemble of bubbles, is the framework that makes it most natural. The third version of the multiverse doesn't come from cosmology at all. It comes from a puzzle that has sat at the heart of quantum mechanics since the theory was first developed in the 1920s, a puzzle about what physics is actually saying happens when someone makes a measurement. Quantum mechanics describes the behavior of matter and energy at the smallest scales: atoms, electrons, photons, the fundamental particles. It is the most precisely tested theory in the history of science. The predictions it makes about the outcomes of experiments have been confirmed to extraordinary precision, in some cases to more than 10 decimal places. There is no doubt that the theory works. The question is what it means. In quantum mechanics, a particle doesn't have a definite position or a definite energy or a definite spin direction before it's measured. It exists in a superposition, a blurring of all its possible states at once, described by a mathematical object called a wave function. The wave function evolves in time according to the Schrödinger equation, a perfectly deterministic law. But when you measure the particle, when you look at where it is or what its spin is, the wave function appears to collapse instantly into a single definite state. Before measurement, superposition. After measurement, one specific outcome. This collapse is the problem. It's not described by the Schrödinger equation. It happens during measurement, but there's no precise definition of what counts as a measurement. Why does a particle have no definite position until you look, but then it does once you've looked? What's special about looking? The theory tells us how to calculate the right answer. It doesn't tell us what's actually happening. In 1935, Erwin Schrödinger, one of the founders of quantum mechanics, devised a thought experiment that made the problem as vivid as possible. Imagine a cat in a sealed box with a tiny amount of radioactive material connected to a detector. If the detector registers a radioactive decay, a quantum event, it triggers a mechanism that kills the cat. Quantum mechanics says the radioactive atom exists in a superposition of decayed and not decayed until observed. If the cat's fate is tied to the atom's quantum state and the atom is in superposition, is the cat both alive and dead? Schrödinger intended this as an argument against taking quantum superposition too literally, a demonstration of how absurd the theory seemed when applied to everyday objects. Niels Bohr and the Copenhagen school had an answer. The superposition exists at the quantum scale, but measurement causes collapse into one definite outcome. When you open the box, you find the cat definitely alive or definitely dead. The other possibility vanishes. This answer works for calculations. But where does the vanished possibility go? What exactly is a measurement? Why does the act of looking at something change what it does? Bohr's reply was essentially pragmatic. The theory gives predictions, and the predictions are correct. Use the theory and stop asking what it means. This attitude served physics well for decades because quantum mechanics kept producing right answers and the experimenters kept confirming them. But for a Princeton PhD student named Hugh Everett III, the pragmatic answer wasn't satisfying. Everett was born in 1930 in Washington, D.C. He was extraordinarily mathematically gifted, the kind of student who understands things quickly and doesn't accept frameworks he finds logically incomplete. In 1955, at 24, working under John Wheeler, he was thinking about quantum cosmology, how to apply quantum mechanics to the entire universe. The Copenhagen interpretation has a fundamental problem with that goal. It requires an observer external to the quantum system to cause collapse, but if the system is the entire universe, there is no external observer. There's nothing outside the universe to look at it and collapse its wave function. The Copenhagen picture breaks down at the largest possible scale. Everett's solution was radical in its simplicity. He proposed that the wave function never collapses. The Schrödinger equation is always right, without exception, for everything, including macroscopic objects and observers. When you open Schrödinger's box and look at the cat, you become part of the quantum system. You interact with the cat's state. The system as a whole, you plus the cat plus the detector plus the air in the room plus the photons your eyes receive, evolves into a superposition. In one branch of that superposition, you find the cat alive. In the other, you find it dead. Both outcomes happen. Both versions of you exist. They simply can't interact with each other afterward because the two branches of the wave function have diverged too far to ever overlap in any measurable way. The universe doesn't collapse into one outcome when you make a measurement, it branches. Every quantum event that has more than one possible outcome produces a split. You live in one branch, another version of you lives in another. Neither branch is more real than the other. They're just different parts of a single quantum state that is growing more complex and branching more rapidly with every passing moment. Everett submitted his dissertation to Wheeler in 1956. Wheeler thought the idea was brilliant but worried about how it would be received. He arranged for Everett to visit Copenhagen and discuss the work with Niels Bohr. It did not go well. Bohr's school was not interested in an interpretation that kept all the outcomes at the cost of multiplying the number of worlds into an incomprehensible profusion. Everett revised the dissertation, softening some of its claims, and the shorter version was published in 1957. It landed almost without impact. A handful of physicists read it. Almost none responded. Before the dust had even settled, Everett accepted a job at the Pentagon working on Cold War defense research, applying game theory and mathematical modeling to questions of nuclear strategy, some of which were classified for decades. He left academic physics without a backward glance and never really returned. He died in 1982 at 51 from a sudden heart attack. He had spent the intervening years doing defense consulting, becoming wealthy enough to indulge his love of expensive food and drink, and watching his idea slowly gather momentum in his absence. The revival began in 1970 when Bryce DeWitt of the University of North Carolina wrote an article in Physics Today, a general audience physics magazine, enthusiastically promoting Everett's framework under the vivid name Many Worlds. DeWitt wrote that every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe is splitting our local world on Earth into myriads of copies of itself. This kind of language was striking and memorable, and it caught on. Wheeler organized a conference on the topic in 1977, and he persuaded Everett, who had all but vanished from physics, to attend. Everett presented his ideas publicly for essentially the first time to a room full of physicists who were finally taking them seriously. He seemed bemused by the attention. 5 years later, he was dead. Today, the many worlds interpretation is one of the most debated frameworks in foundational physics. David Deutsch at Oxford, who pioneered the field of quantum computing partly because he believed the existence of a working quantum computer would provide evidence for parallel branches, has argued for decades that it's the only complete and consistent interpretation of quantum mechanics. Sean Carroll at Johns Hopkins considers many worlds the most natural and honest reading of what the equations say. Poll results among physicists vary widely depending on how the question is framed, but a substantial and growing fraction of those who think carefully about foundations take many worlds seriously. The many worlds interpretation is the level 3 multiverse, and it's worth being clear about what it does and doesn't say. The branches in the many worlds picture are not spatially separate regions of space. They don't each have their own sky, their own stars, their own galaxies, located somewhere out there in a different part of a larger space. They're branches of a single quantum state, the universal wave function. The split happens in the abstract mathematical space that describes all quantum possibilities, not in physical space. From inside any branch, you experience a single definite reality. You never feel yourself splitting. You have no access to the other branches. The other versions of you are not elsewhere. They're in a different part of the same quantum structure. In Tegmark's framework, the level 3 multiverse doesn't actually add new universes beyond what levels 1 and 2 already contain. What it does is add additional branches within each existing bubble universe. Every quantum event in every bubble generates branches. The total number of branches, if you're counting those, is essentially incalculable, and whether those branches are real is still genuinely an open question. If eternal inflation provides a mechanism for bubble universes, the next question is, how different can the physics in those bubbles actually be? What determines the range of possible laws? This is where string theory enters the story, and where the numbers involved become almost impossible to process. String theory is the leading candidate for a theory of quantum gravity, a framework that would unify Einstein's general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which governs the behavior of matter at the smallest scales. These two theories are mathematically incompatible in their current forms. You cannot use both simultaneously to describe a singularity inside a black hole, or the first instant of the Big Bang, where both gravitational and quantum effects are extreme. String theory proposes a solution. The fundamental constituents of nature aren't point-like particles, but tiny one-dimensional vibrating strings of energy. Different vibrational patterns correspond to different particles: an electron, a photon, a graviton, the way different vibrations of a guitar string produce different notes. One specific vibrational pattern corresponds to the graviton, the particle that carries gravity. This is why string theory is primarily interesting as a theory of quantum gravity. It includes gravity naturally, rather than having to bolt it on. The mathematics of string theory works out to produce a consistent framework for quantum gravity. But it comes with a requirement. The universe needs more dimensions than the 4 we experience. Depending on the version, the equations demand 10 or 11 dimensions of space-time. We experience 3 of space and 1 of time. The remaining 6 or 7 dimensions the theory proposes are compactified, curled up on themselves at scales so small they're completely undetectable with current technology, or likely with any foreseeable technology. They're wrapped up tighter than atoms, smaller than anything we have instruments to probe. The shape and topology of those hidden dimensions matters enormously. The geometry of the extra dimensions determines the physics in the 4 dimensions we can see, the strength of gravity, the masses of fundamental particles, the values of all the constants. All are determined, in string theory, by the particular way the extra dimensions are curled up. Change the shape and you change the physics, and here's the problem, or the opportunity, depending on your perspective. The number of distinct ways those extra dimensions can be compactified is not small. The estimates vary considerably depending on the specifics of the calculation, but the most commonly cited figure is approximately 10 to the power of 500. Leonard Susskind of Stanford, one of the founders of string theory and one of the field's most influential living practitioners, coined the term the landscape in 2003 to describe this enormous collection of possible configurations, borrowing the metaphor from evolutionary biology's fitness landscape. Each configuration corresponds to a stable vacuum state, and each vacuum state corresponds to a different possible set of physical laws. The number 10 to the power of 500 deserves a moment of genuine attention because it's the kind of figure that looks like a big number and actually is one in a way that resists all intuitive handling. The total number of atoms in the observable universe is roughly 10 to the power of 80. The number 10 to the power of 500 is larger than that by a factor of 10 to the power of 420. If you wrote one configuration per atom in the entire observable universe, and then did that again and again, filling every atom in the observable universe with a completely fresh tally each time, you would need to repeat the exercise more than 5 times before reaching the end of the list. In any meaningful sense, it is infinite. The mathematician in the room might insist it's technically finite, and they'd be right, but the practical difference is 0. Washington Taylor at MIT, working with collaborators on a more detailed analysis of the string theory vacuum in 2015, calculated that the true number of distinct configurations might be far larger still, something in the range of 10 to the power of 272,000. That's not 272,000 times larger than 10 to the power of 500. It's 10 to the power of 500 raised to a power of over 500. The original estimate suddenly looks modest. Each of those configurations corresponds to a different possible universe, with different particle masses, different force strengths, different constants. Some of those universes would collapse immediately. Some would expand so fast that nothing ever forms. Some would have no atoms, no chemistry, no anything recognizable as structure. Most of them, by any reasonable accounting, would be empty and featureless within moments of their formation. A relative handful, but still an enormous absolute number, would have physics compatible with the formation of stars, planets, and chemistry. The landscape connects to eternal inflation in a way that many physicists find either beautiful or disturbing. If inflation is eternal, and the inflaton field decays differently in different bubble universes, then each bubble's physics is determined by which valley of the string landscape it settles into. With infinitely many bubbles, every valley gets realized somewhere. Our universe is one of those bubbles, the one whose particular configuration of hidden dimensions happen to produce physics compatible with our existence. Most bubbles won't have our physics, but we could only find ourselves in one that does. For the fine-tuning problem, this provides an answer of a kind. The apparent precision of the cosmological constant and of all the other constants isn't miraculous. In a landscape of such enormous variety, combined with an infinite ensemble of bubble universes each realizing a different point in that landscape, the existence of some universes with just the right constants is inevitable. We're in one of those universes not because we were selected, but because the others don't have observers to ask the question. The scientific discomfort is substantial, and it's legitimate. String theory has not yet produced a confirmed experimental prediction in spite of decades of development. The supersymmetric particles it predicts have not been found at the Large Hadron Collider. The landscape itself is currently a mathematical structure, not an observational one. And a theory that explains the fine-tuning of our universe by positing an infinity of unobservable other universes can, to a certain frame of mind, look less like a scientific explanation and more like a way of declaring the problem unanswerable. There are physicists who feel exactly that way and who say so without apology. But the defenders of the landscape argument, and there are serious defenders, including Susskind, Guth, and many others, point out that the fine-tuning problem is real, not imaginary. The cosmological constant really is 122 orders of magnitude smaller than quantum field theory predicts. That discrepancy exists regardless of whether you like the landscape or not. The question isn't whether the problem is there, it is. The question is whether the landscape is a better answer than the alternatives, which currently amount to we don't know, or it will eventually be explained by a deeper theory we haven't found yet. Max Tegmark's framework ends at level 4, and this is where physics shades into philosophy, and then in a very strange move tries to shade back into physics again. The level 4 multiverse doesn't come from inflation or quantum mechanics or string theory. It comes from a question about mathematics itself. A question that physicists usually take for granted, but that, when examined directly, turns out to be deeply strange. Here's the observation. When physicists describe the universe, they write equations. The behavior of an electron in a magnetic field is described by an equation. The curvature of space-time around a massive body is described by an equation. The way light spreads through a medium is described by equations. The evolution of the universe from its very earliest moments to the large-scale structure we observe today is described by equations. And those equations work with extraordinary precision. They work in circumstances far beyond those in which they were first developed. They predict phenomena that nobody knew existed before the math pointed toward them. The planet Neptune was calculated to exist before anyone had looked in the right direction to see it. The existence of the Higgs boson was predicted from mathematics decades before any accelerator could produce one. Gravitational waves were predicted by Einstein's equations in 1916 and detected exactly as the math described a full century later. This success is not obviously expected. Why should a universe made of matter and energy obey precise mathematical rules? Why should equations scratched out by humans on paper describe the behavior of distant galaxies that have never interacted with a human, or the interior of a black hole where no observer could survive? The physicist Eugene Wigner addressed exactly this question in a famous 1960 essay he titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." His point was that the connection between abstract mathematics and physical reality is itself a mystery, one that physicists use constantly but almost never pause to examine. Tegmark's answer is that the connection isn't a mystery because it isn't a connection at all. He proposes that the universe doesn't just obey mathematical rules, it is a mathematical structure. Physical reality and a specific mathematical structure aren't two separate things, one being a description of the other. They are the same thing. There is no physical world behind the equations that the equations are pointing at. The equations are the world. What we experience as matter, space, time, and energy are properties of the mathematical structure itself. If that's true, a natural question follows: what makes our mathematical structure special? Why does this set of equations get to be real while other perfectly valid mathematical structures remain purely abstract? If the universe is a mathematical structure and we have no special reason to think this particular structure is privileged over others, then Tegmark argues there's no principled basis for treating them differently. All mathematical structures that are self-consistent should be equally real, not metaphorically, not as a metaphor for saying they could exist, actually physically real as our universe is to us. This is the mathematical universe hypothesis. It's the level 4 multiverse. And what it contains is genuinely beyond the reach of current human imagination to fully picture. Not just universes with different constants, not just bubbles with different particle masses, but universes with entirely different kinds of physics. Universes with more or fewer dimensions. Universes where time doesn't flow in the same direction. Universes where the relationship between cause and effect works differently. Universes built from mathematical structures that have no overlap at all with the mathematics of our physics. Some of these structures would be too simple to contain anything we'd recognize as complexity or life. Others might be so alien that the word life wouldn't apply in any way we could map to our own experience. Tegmark argues that the level 4 multiverse is actually the most parsimonious version of the idea, the one requiring the fewest unexplained assumptions. In the standard picture, our universe exists and others don't, which raises the question, why? What makes our mathematical structure the special one that gets to be real? The level 4 hypothesis dissolves that question by saying none of them are special. They all exist. There's no why this one because there's no selection. Everything that can exist does exist. The ancient philosophical question, why is there something rather than nothing, also transforms in this picture. The answer is simply that nothing, a state in which no mathematical structures exist, is itself a mathematical concept, and if all mathematical structures exist, then the absence of mathematical structures doesn't. Nothingness is ruled out by the same logic that includes everything else. Whether this is a genuinely satisfying answer or a philosophical sleight of hand is a question each person can only answer for themselves. Most physicists treat the level 4 multiverse as a provocative and thought-provoking framework rather than a scientific theory in the usual sense, and with good reason. It makes no predictions that could be tested even in principle with any conceivable technology. But it earns its place in this discussion because it's the honest destination of the logic that got us here. Follow the implications of taking physics seriously all the way to their conclusion, and this is where you end up. It's the outermost boundary of what the idea of all possible universes could mean. The obvious problem with every version of the multiverse, in almost every form, is that the other universes lie beyond observation by definition. The cosmic horizon seals off level 1 regions. The inflating space between bubbles in level 2 ensures that bubble universes can't communicate with each other. The decoherence that separates level 3 branches prevents any interaction between them, so what, if anything, could we look for? There is one genuine exception, specific to the level 2 bubble multiverse. If eternal inflation is producing bubble universes continuously, then in the very early history of our universe, when the bubbles were newly formed and before inflation pushed everything apart, 2 bubbles might occasionally have been close enough to collide. The collision would have sent a shock wave through our early universe's space, leaving a specific, geometrically precise signature in the cosmic microwave background. A circular ring where the temperature fluctuations look slightly different from the surrounding sky. The signature would be circular because the collision zone is spherical, and we'd be seeing it in cross-section, the same way a sphere intersecting a flat plane always produces a circle. This is a real prediction of some bubble multiverse models, and it can be searched for with real telescopes. In 2011, a team led by Hiranya Paris at University College London performed a systematic search of the WMAP data, specifically looking for the statistical fingerprints of bubble collisions. They found no statistically significant evidence. Later analysis of the higher-resolution Planck satellite data reached similar conclusions. The absence of the signal doesn't prove the bubble multiverse doesn't exist. Our bubble might simply have had no close neighbors, or the signal might be too faint for current instruments, or our particular position in the bubble might not have been in the path of any collision wave, but the signature hasn't appeared. Some physicists are working on related approaches using the statistics of the CMB itself. If our bubble universe formed inside a larger inflationary background, there might be subtle statistical anisotropies in the CMB, slight differences in the pattern of fluctuations depending on which direction you look. These would be different from the bubble collision rings, more like a gentle preferred direction baked into the structure of the early universe. There are hints of such anomalies in the Planck data, features like the so-called axis of evil, a suspicious alignment of certain large-scale CMB patterns that has been known since the WMAP days. But the statistical significance is disputed and the interpretation is contested. None of it comes close to being a confirmed signal. Roger Penrose, the British mathematician and physicist who shared the 2020 Nobel Prize in Physics for his work on black holes and singularities, has proposed a different approach, not looking for collisions between bubbles, but for evidence that our universe isn't the first in a sequence. His theory, conformal cyclic cosmology, proposes that the universe goes through repeated cycles: Big Bang, expansion, cooling, heat death, followed by a new Big Bang. In his model, the final stages of a previous cycle, specifically the evaporation of supermassive black holes near the heat death of that universe, would leave faint traces in the CMB of the next cycle, appearing as unusually low-variance circular regions in the data. Penrose and his collaborators named these features Hawking points in honor of Stephen Hawking. They claimed in 2018 to have detected them in the Planck data. Other groups reanalyzed the same data and concluded the patterns were consistent with random fluctuations in the noise within the range expected by chance without needing to invoke previous cosmic cycles. The original team disputed those conclusions. The debate is still active in the peer-reviewed literature, and the question of whether the Hawking points are real or artifacts of analysis has not been conclusively settled. Beyond these attempts, the multiverse remains formally untestable in any direct sense with any instrument that currently exists or is reasonably foreseeable. Not because the right telescope hasn't been built yet, but because the physics that generates other universes, in most of their forms, also seals them off from us in ways that don't yield to technological improvement. The cosmic horizon retreats as the universe ages but never disappears. The inflationary separation between bubbles grows faster than any signal can cross. The decoherence that seals off quantum branches is in some formulations fundamentally irreversible. This is the most honest thing that can be said about the experimental status of the multiverse in the mid-2020s. The searches are real, the theoretical predictions are specific enough to be looked for, and so far nothing has been found. That could change. Physics has a history of delivering evidence for things that once seemed permanently unreachable, gravitational waves rippling through detectors after a century of theoretical prediction, the Higgs boson finally appearing at the LHC after decades of searching, the cosmic microwave background discovered accidentally by engineers pointing an antenna at the sky. But it can also be the case that some questions genuinely lie beyond the horizon of what observation can ever tell us. The multiverse may be one of those questions. Whether that places it inside or outside the boundaries of science is a debate that will likely outlast the current generation of physicists working on it, and it may be one of the most important methodological debates the field has ever had. It would be misleading to present the multiverse purely as an exciting frontier of theoretical physics, without acknowledging that serious, distinguished scientists think it has gone wrong in ways that matter. The objections aren't from outsiders or people unfamiliar with the physics. They come from physicists who have spent careers on exactly these problems, and they deserve to be heard clearly. Paul Davies, an Australian theoretical physicist at Arizona State University, who has written extensively on the philosophy of cosmology, made a pointed argument that invoking an infinity of unseen universes to explain the features of the one we observe is exactly as ad hoc as invoking an unseen creator. His point is that the multiverse doesn't actually explain fine-tuning, it just relocates the mystery. You still have to explain why the multiverse has the structure and properties that allow it to generate universes with the right physics. Why does the landscape of string theory contain any valleys compatible with life at all? Why does eternal inflation generate bubbles that realize those valleys? The deeper question retreats one level but doesn't disappear, and Davies argues that's not an explanation, it's a deferral. George Ellis is a South African cosmologist who collaborated with Stephen Hawking on some of the foundational mathematical work in relativistic cosmology in the 1970s, and he has been one of the most persistent and philosophically careful critics of the multiverse. Ellis has argued that the multiverse has crossed a line from physics into metaphysics, That calling it science because it follows mathematically from established theories is a category error. Science, in the tradition that has made physics so successful, requires theories that make predictions that could in principle be falsified. You have to be able to be wrong. A theory that predicts the existence of entities that can never, in any conceivable circumstance, be observed or detected, a theory that is immune to any possible disconfirmation, is not a scientific theory in the sense physics has always required. It is a metaphysical proposition dressed in the language of physics. The mathematics may be valid. Whether the physical interpretation follows is a completely separate question. Paul Steinhardt, who helped develop inflation in the 1980s and spent decades contributing to it, eventually became one of its most vocal critics. His objection is specifically about eternal inflation and the multiverse it generates. A theory that says everything that can happen does happen, somewhere in some bubble, has no power to explain why we observe what we observe. If every possible value of the cosmological constant is realized in some bubble, then the fact that we observe our particular value is neither surprising nor predicted. The theory is compatible with any observation at all. And a theory compatible with every possible observation is, in a logical sense, a theory that predicts nothing. Steinhardt has proposed alternative cosmological frameworks, most notably the cyclic model developed with Neil Turok, that aim to explain the large-scale features of the universe without requiring eternal inflation or an infinite ensemble of bubble universes. These critics are not wrong to raise these concerns. The testability problem is real. The tendency of certain multiverse advocates to count the math as evidence for the physics, to treat the existence of other universes in the equations as confirmation of their physical existence, is a philosophical step that many find unjustified. The history of physics includes many beautiful mathematical theories that turned out not to describe reality. Mathematics is a tool for describing the world, but not every mathematical structure corresponds to something real. Knowing which ones do is the work of experiment, and experiment is exactly what the multiverse resists. The defenders' response is that the multiverse isn't a choice. They didn't want it to be there. It showed up as a consequence of inflation, quantum mechanics, and string theory, three separately motivated frameworks. You can object to the multiverse, but then you have to deal with the fine-tuning problem, and the measurement problem in quantum mechanics, and the naturalness problems in particle physics, without the tools the multiverse provides. Those problems are real too. There are no clean solutions on either side. Pulling all of this together, the honest answer to the question, how many multiverses are there, turns out to depend almost entirely on which framework is considered, and the frameworks don't almost all agree. In the level 1 picture, there is one universe that is simply much larger than what we can see, perhaps infinitely so. Within it are infinitely many regions similar to ours, with every possible history eventually repeated. This is the most conservative version of the multiverse. It emerges naturally from the cosmological data we have, requires no new physics, and is in that sense the least speculative of all the versions. Many cosmologists accept it as a reasonable implication of well-established observational results, even if they rarely spend much time thinking about the copies of themselves that inevitably follow. The level 2 bubble multiverse depends on whether inflation is eternal. The mathematics of the most natural and least fine-tuned inflationary models all point toward eternal inflation. If those models are correct, then there are infinitely many bubble universes, each with potentially different physics. The level 2 multiverse is not confirmed, but it emerges naturally from a framework that is well supported. The bubble universes are separated from ours by an inflationary sea that no signal can cross, which places them permanently outside observational reach. And that fact sits at the center of the ongoing scientific debate about whether the theory is science or metaphysics dressed in the language of science. The level 3 many worlds multiverse is either true or false, depending on which interpretation of quantum mechanics correctly describes reality. If the wave function never collapses and the Schrödinger equation is universally valid, then the number of branches is beyond counting, effectively infinite, and growing at a rate driven by quantum events occurring everywhere in the universe simultaneously, in every atom, in every particle, in every photon. If the Copenhagen interpretation or some alternative is correct, there are no branches at all. The two options are compatible with exactly the same experimental results. At present, we don't know which is right, and there is genuine disagreement in physics about whether the question can ever be experimentally decided. The level 4 mathematical universe is the most speculative. It either contains literally every possible mathematical structure as a real universe, or it's a philosophically interesting framework that happens to be consistent with physics without adding anything physically meaningful. There's currently no known path to testing it, and many physicists would say there never will be, that the level 4 multiverse lives by its own construction permanently outside the domain of science. What all 4 levels share is something worth sitting with. None of them was invented for its own sake. Whether any of these destinations correspond to physical reality is a question that may not be settled in our lifetime. The physics that generates the other universes, in most versions, is also the physics that hides them from us. And hiding them isn't an incidental feature, it's structural. That leaves us in an unusual position. The question, how many multiverses are there, has not one answer but at least 4 nested inside each other, arising from different branches of physics disputed by serious people on serious grounds and entirely untested by direct observation. It's a frontier, not a settlement. And the most honest thing anyone can say about it is that we are living in the middle of one of the most ambitious and unresolved questions in the history of science. The question, how many multiverses are there, might seem like the kind of thing that only theoretical physicists could care about, abstract, unverifiable, irrelevant to daily life in any direct way. But embedded in it are some of the deepest questions humans have ever asked about the nature of existence, and the answers, even the speculative ones, change how physicists think about fundamental problems. What we can say with confidence is that the observable universe, the 93 billion light-year sphere centered on Earth, with its 2 trillion galaxies and its hundreds of billions of stars per galaxy and its countless planets and its at least one confirmed instance of intelligent life, is already, by any measure, one of the most complex and richly structured things that physics describes. And if the physics is right, it may be the smallest possible part of all that exists. Whether there are other universes is a question that may not be answerable in any human lifetime, or any lifetime at all. But it's a question that has already changed the way physicists think about physical law, about probability, about the relationship between mathematics and reality, and about what it means for something to exist at all. The question is productive even when it can't be answered. It reveals the structure of what we know, the edges of what we can know, and the vast unknown landscape beyond those edges. Part of what makes the multiverse debate so compelling, even for those who remain skeptical, is that they force a confrontation with questions that science usually manages to sidestep. Why does anything exist? Why are there laws at all? Why are those laws the specific ones we observe rather than different ones? Physics has always quietly assumed an answer to these questions and moved on. The multiverse is what happens when you refuse to move on, when you insist on looking directly at the assumed answer and asking whether it holds up. Sometimes it does. Sometimes you find something underneath it that you weren't expecting. Giordano Bruno asked similar questions in the 16th century. He had no equations, no telescopes, no particle accelerators, and no cosmic microwave background maps. He had only a restless refusal to accept that the observable world was all there was, and a willingness to pay a significant price for saying so publicly. The physics has changed immeasurably since then. The fundamental restlessness behind the question hasn't changed at all. Whether the next displacement, from the only universe to one of infinitely many, follows the historical pattern is a question we're living in the middle of. The answer, whatever it turns out to be, will be one of the most consequential things physics has ever told us about the nature of what is real. If questions like this are the kind you want to keep exploring, then subscribe. Every video on this channel goes this deep into the science, the history, the people who built the ideas, and the honest uncertainties that remain. There is a lot more to cover, and this is exactly the right place to cover it.